Hey everyone, and welcome back to another deep dive. You know how this works. You send us a stack of sources and we dive deep.
That's right.
This time around, we're taking a look at transformer expressivity.
Yeah,
And wow, you guys really sent us some dense material. Um,
absolutely.
Lots of academic papers. We've got formal languages, computational models, even some circuit diagrams.
Yeah,
So it's clear you're looking for something a bit more than just like a surface level explanation this time.
absolutely. Really trying to understand the nuts and bolts of how researchers are approving these capabilities, the algorithms involved, even the nitty-gritty of the mathematical formulas.
All right, well, challenge accepted. But before we get too lost in the weeds here, let's set the stage for our listeners. What exactly are transformers? In the AI sense of the word.
Yeah, so think of them as a special type of neural network. They've become like the workhorse of many AI systems, especially the ones that deal with language. And what makes them unique is their reliance on these attention mechanisms.
Attention. So, like, can a transformer tell if I'm zoning out during this episode?
Not quite. Attention in this context is about how the model focuses on different parts of the input. Like, imagine you're reading a sentence, but some of the words are highlighted in bold. And those are the words that are most important for understanding the overall meaning. So transformers are doing something similar, but they do it with sequences of data, like the words in a sentence.
Okay, that makes sense. So they're like super readers, picking out the key information.
Yeah, that's a great way to put it. Now, there are different kinds of transformers, like encoder only, decoder only, and encoder decoder models, each with specific purposes, but that attention mechanism is what unites them.
All right, so we've got our super readers. Now, where do these formal languages come in?
So that's where we start to connect transformers to the world of theoretical computer science. Formal languages are essentially sets of strings, and they're defined by very precise rules, like the grammar of a programming language or even a mathematical formula, which has a very specific structure. These are all examples of formal languages.
So we're testing if transformers can learn grammar or do math.
In a way, yes. But more importantly, formal languages help us categorize different types of computational problems. So this lets us figure out what's easy or hard to solve. And by studying whether transformers can recognize or generate these languages, we can start to understand the limits of their computational power.
So it's like setting up an obstacle course for transformers and seeing how far they can get.
That's a great analogy. And what's fascinating is that researchers have started to uncover this pattern, and it seems like there are three distinct levels of expertivity in transformer.
3 levels. Intriguing. Tell me more.
At the highest level, some transformers, particularly decoders that can take many intermediate steps, kind of like performing calculations on a scratch pad, seem to be as powerful as a Turing machine.
Wait, a Turing machine? Isn't that the theoretical model of computation that can solve any problem?
Exactly. So theoretically, these transformers are incredibly powerful.
Wow. So even the most complex problems are fair game for these top-tier transformers.
Theoretically, yes. Of course, in the real world, there are always limitations, like how much data we have or how much computing power we can throw at a problem.
Okay, that makes sense. What about the other 2 levels?
Well, at the very bottom, we have transformers that are quite limited. These tend to use very simple attention mechanisms, and they can only handle a very small set of problems.
So like computational toddlers just starting out.
In a way, yeah, they can handle some very basic tasks, but they struggle when things get more complex.
Right, so we have the computational superheroes and we have the toddlers. What about the transformers in between?
That's where things get really interesting. Many commonly used transformers fall somewhere in the middle. They're definitely more powerful than the simplest ones, but they likely can't solve the very hardest problems. And this middle ground is where a lot of the current research is focused.
Sounds like we have a lot to unpack. Let's dive into the details of these 3 levels.
Let's do it. And trust me, we'll get into the algorithms and the proofs that are at the heart of these discoveries. Welcome back to our deep dive into transformer expertivity.
All right, let's jump right back in. We've got these 3 levels of computational power and transformers. I'm eager to explore the research that backs all this up.
Absolutely. Let's start by delving deeper into those top tier transformers, the ones that can potentially reach Turing machine levels of power.
The computational superheroes. What makes them so special?
One key insight comes from a 2021 paper by Perez and colleagues. They showed that if you take a transformer, an encoder decoder, and give it certain types of positional embeddings and allow it to take an unlimited number of intermediate steps, it can actually simulate a Turing machine.
Wait, so they built a transformer that could theoretically solve any computational problem.
That's the remarkable implication of their findings. Of course, this is in a theoretical sense, but it really highlights the incredible potential within these models.
Okay, my mind is officially blown. Now, you mentioned positional embeddings. What are those and how do they play into this?
Think of positional embeddings as a way to give the transformer information about the order of the elements in a sequence. So it's like adding these little tags to each word in a sentence to tell the model, like, this is the first word, this is the second word, and so on.
So it's like giving the transformer a sense of grammar.
In a way, yeah, it helps the model understand not just the words themselves, but also their relationships to each other.
That makes sense. And what about these intermediate steps you mentioned? Why are they so important?
Well, they're crucial because they allow the transformer to perform more complex computations. It's like giving the model a scratch pad to work on. So instead of just taking the input and producing an output directly, it can perform a
Whoa, did someone just break the fourth wall? Let's hear it.
Hey, can we focus on the complexity expressive of the transformer?
Hey there. Absolutely. We can definitely narrow our focus.
Yeah, diving into expressivity is where it gets interesting.
So you want to really understand what makes some...
Transformers more powerful than others, right?
All right, let's do it.
Well, it's helpful to think about the resources available to them.
Exactly. So how many resources do we give it?
Let's begin by talking about those intermediate steps.
Perfect. This was something we were going to get to.
They allow the transformer to perform complex computations. It's like giving the model scratchpad to work on.
So the transformer is thinking things through step by step.
Precisely. The more intermediate steps you allow. Absolutely. We can definitely zoom in on expressivity.
Yeah, let's do that. So how about we focus on what transformers can and cannot do?
Exactly. Expressivity is all about the range of tasks a transformer can handle.
Okay, so what determines how expressive a transformer is?
Great question. Several factors come into play here.
Lay 'em on me.
Things like the type of attention mechanism it uses,
Okay,
the architecture, whether it's encoder, decoder, or encoder-decoder,
makes sense.
and, as we mentioned before, the ability to take intermediate steps.
Got it. So the more complex these features, the more expressive the transformer. The more complex reasoning the transformer can perform.
In Paris's paper, they showed that with enough intermediate steps,
A transformer can simulate the behavior of a Turing machine.
which can solve any problem algorithmically, as we know.
So it is like unlocking the full potential of the transformer's brain.
But this is theoretical, so what are the practical limits?
Great question. In reality, we don't have unlimited data.
Or unlimited computer power, so even if the transformer might theoretically be able to solve any problem,
In practice, we might not be able to train it effectively.
exactly, we might not be able to give it the resources it needs.
Okay, it's like having a supercomputer with a tiny power source.
Precisely. But the fact that transformers can theoretically reach this level of computational power is huge. Generally, yes, but it's not always a linear relationship.
Interesting.
Like some transformers might be excellent at one specific task,
Okay.
but struggle with others even if they seem similar.
So it's about finding the right tool for the job. So it means the potential is there waiting for us to unlock it.
Okay, now let's look at some transformers at the bottom.
Right, let's zoom in on their limitations.
You see, researchers have found that these are quite limited.
I mentioned parity and IQ1 earlier.
Yeah, that's an example of something simple transformers can't do. Precisely.
Okay, so let's dive into those different levels of expressivity.
All right, let's start with the lower bounds of transformer expressivity.
The computational toddlers.
Exactly. So what can these transformers do?
Well, based on the papers, it seems like they can handle some basic formal languages.
Yeah, like the ones recognizable by AC circuits.
AC, okay, let's unpack this. What are AC circuits?
Think of them as very simple circuits. They operate on binary values
Got it.
and can perform basic logical operations like and, or, and not.
Okay, so pretty limited in what they can do. Can you remind me what parity is all about?
Sure, so you've got zeros and ones, and you have to determine whether the number of ones is odd or even.
It seems easy enough.
Right, but transformers with simple attention can't do it reliably.
They don't have the machinery to keep track of the count.
Well, they're working with limited resources.
Okay, parity's out. What about the DYCK1 problem?
So that's a language of correctly balanced parentheses.
It's like where every open has a closing one.
Right, transformers can't handle it. They get confused.
So even though these problems seem easy to us humans,
They expose fundamental limitations in basic transformers. Exactly. So transformers that are equivalent to AC circuits
okay.
can only recognize languages that can be processed with these simple operations.
So what kind of real-world tasks fall into this category?
Well, you might see these transformers handling simple pattern matching.
Researchers have formally proven this limitation, right?
Yes, by showing that these transformers fall within AC1.
Okay, now that sounds like technical jargon.
Okay, so AC1 is problem solved by relatively simple circuits.
So these basic transformers are simple
A
circuits.
great way to think about it. Or basic classification tasks where the relationships are straightforward.
All right, that makes sense. What about the upper bounds?
Now we're getting into what transformers cannot do.
The limitations.
Right. One important area of research focuses on proving these limits.
How do researchers go about doing that?
They often use techniques from circuit complexity theory
Okay.
or formal language theory to show that certain problems
Yeah.
would require a transformer to have infinite resources.
Oof, that's a pretty hard stop. All right, so that's the bottom. What about in the middle?
Okay, that's where it gets more exciting and mysterious.
I know that these are more powerful than AC transformers.
Correct. They can solve problems like majority.
That's about determining if most bits in a string are ones.
And that's something hard attention transformers cannot do. It is. This tells us that no matter how big or well-trained a transformer is,
Right.
it will never be able to solve those particular problems.
So what are some examples of problems that are beyond the reach of most transformers?
Well, some research suggests that recognizing certain context-sensitive languages
Okay.
or performing complex arithmetic calculations might be too difficult
All right.
for transformers without the right architecture or attention mechanisms.
Okay, so now we've seen the boundaries, what these models can and cannot do.
Exactly. And by focusing on expressivity, we can better understand how to design.
But the upper limits of middle transformers are still being explored.
Yes, pinning down their limits is an active area of research.
Sounds like there's a lot we still don't know.
Absolutely. But there are intriguing clues, for example.
Research has shown that average heart attention can be simulated.
Yes, by circuits known as TC0.
TC0, so a step up in computational power.
Exactly. TC0 circuits include a majority gate.
Ah, so that's why transformers can solve the majority problem.
Exactly.
So we've got middle-level transformers bound by TC0.
Precisely. And applied transformers to solve real-world problems.
Absolutely. It's all about knowing the tool's capabilities.
And its limitations.
Well, that's all the time we have for today.
Thanks for joining us for this exploration of transformer expressivity.
We hope you found it insightful.